Let's talk about nuclear reactions. We're going to follow very specific rules when we balance nuclear reactions. So let's first talk about radioactive decay. There are several different kinds of radioactive decay. We're going to focus on the first three ones: the alpha particle decay, beta particle decay, and positron emission. You need to remember the symbol for each of these particles, and I personally like to use these three over here, but you will find them in this fashion as well. So be familiar with both depending on what the question, how the question is written. You need to be able to determine or to figure them out. So remember the symbol very well and which symbol goes with which particle, especially these two, because students tend to mix these two up because they're so close to each other. One just has a +1 and one has a -1. So remember what they are. That will be essential to you learning how to figure out nuclear reactions. An alpha particle really is a helium nuclei of high energy, and it is made of 2 neutrons and 2 protons. So every time there's an alpha particle decay, the nucleus is emitting a high energy helium nucleus, so with 2 neutrons and 2 protons, and they're being expelled from the nucleus, which you can see that is reducing the atomic number by 2 because you're losing 2 protons every time. With every alpha particle, you're losing 2 protons, so you can reduce the atomic number Z very quickly. And you're also losing a mass number of 4 because you have a mass of 4 that you're giving off, 2 protons and 2 neutrons. With a beta particle, it's a high energy electron, and this electron is actually being expelled from the neutron, and it's converting a neutron into a proton. So it's got a negative charge associated with it, but you have no mass loss. The positron is the exact opposite of the beta particle. It has the same mass as an electron, so negligible when it comes to talking about mass of neutrons and protons, but it's got a unit of +1. It's a positive charge. I know it's kind of interesting to talk about a positive electron, but that's the idea here. You have a particle that has the mass of an electron, but it has a unit of positive charge. And we're not really going to focus on these so much, but just know a proton obviously is a nucleus of a hydrogen atom, because the hydrogen atom only has a proton without any neutrons in its nucleus. And this is how it's denoted. A neutron has got a mass of 1, but it has no charge. And gamma rays, which they're just a very high electromagnetic radiation, but they have no charge and no mass. They don't really affect the mass or the charge, the Z number of a nucleus. They're just very high. It's a very high electromagnetic radiation, actually very harmful for us. So let's talk about how to balance nuclear decay equations. We're going to treat these as mathematical equations with the left side and the right side. And the key point that you have to remember is that the mass numbers on both sides must be equal, and the atomic numbers on both sides must be equal. And as you see here, the helium particle or the alpha particle has a top number which is counted as a mass number, and the bottom number is the Z number, which is counted with the Z number of the element over here. So when I talk about the mass numbers on both sides must be equal, this mass number up here for polonium has to be equal to the mass numbers on both for both of these on this side. The mass number on the right side is the sum of 208 and 4 from the alpha particle. And you can see that gives me 212, which is equal to 212 over here. As I'm looking at the bottom numbers over here, this is my Z number or atomic number for polonium, and it has to be equal to the Z numbers, the bottom numbers on the right hand side. I have 82 plus a 2 gives me 84, which is equal to this number over here, 84. So this is very important to remember when we're doing nuclear decay equations. The top numbers have to be equal to on both sides, and the bottom numbers have to be equal on both sides. And if you think of this arrow as being an equal sign dividing the left side and the right hand side, then you can write this as a mathematical equation where you have 212 over on this side is equal, where the arrow is, equal to 208 plus 4 on the right hand side. And you can do the same thing with the bottom numbers. We will talk about these in detail and go over how to do each nuclear decay equation. But you must remember that the mass numbers and atomic numbers have to be equal on both sides of this arrow or my equal sign here. Let's talk about each of these decays and what it actually does to the atomic mass and atomic number. If I have an alpha decay, that means that I'm losing the equivalent of a helium atom every time I have an alpha decay. That means that my mass number decreases by 4 because this is my alpha particle. It's got a mass of 4 and a Z of 2. So my new element that is formed will have the mass number of the original element minus 4 because that went with the helium atom. So it decreases the mass number of the original element decreases by 4 to give me the mass number of the new element. And the Z number of the new element is equivalent to the original element Z number minus 2 because that's the Z number for the alpha particle or the helium atom. So you note that the new element would have an atomic number that is smaller by 4 from the original element and a Z number that is smaller by 2 from the original element. We will talk in a lot more detail when we do examples on how to balance nuclear decay with alpha decay. Now let's talk about beta decay or beta emission. Remember this has a negative charge. It's an E or a beta, but it has no mass at all. Now this is a charge, but we talk about it as a Z number because what's happening is we're converting a neutron now into a proton, and therefore my Z number is changing. The mass number doesn't change because this is a 0, so the mass number of the new element is the same as the original element, but the Z number increases by 1 because I converted a neutron into a proton, meaning I added one more proton than the original element had. So A is unchanged, but Z, the atomic number, increases by 1 when the element undergoes beta decay. Now let's talk about positron emission. Positron emission is exactly the same, but it has a positive charge, not a negative charge. And therefore what I'm doing here is I'm taking a proton and I'm converting it to a neutron. Therefore my Z, my atomic number, is decreasing by 1 because I'm getting rid of a proton and I'm converting it to a neutron. We can see it shown here. Mass number is unchanged because this positron has a 0 mass number, but my Z decreases by 1 to give me a new Z. That's because I'm converting that proton into a neutron. Remember up here, beta decay, I convert a neutron into a proton, so I increase the number of protons by 1, which is my Z number, my atomic number by 1. Whereas when I have positron emission, I convert a proton into a neutron, so I reduce the number of protons, or the Z number, by 1. Now, I have made several videos that show each of these emissions and how to balance these equations. So I have 1, 2, 3, 4, 5 examples with alpha particle emissions and how to balance these, how to figure out the new element, or how to figure out which emission it is if you're given the original element and the new one, or how to come up with the original element if you're given the new element and the type of decay. So I have the alpha particle emission problems here, I have beta particle emission problems, and I also have positron emission problems. Watch these videos, and if you have any questions, please let me know. But note that I just use a slightly different notation. So be familiar with both. I use the beta with a +1 instead of E for +1. And here I have a beta with a -1 instead of E -1. And here I also use the alpha particle, the alpha with a 4 and a 2 instead of He for helium nucleus. But watch these videos and let me know if you have any questions. The last part of these nuclear equations that we're going to talk about is how to determine by which process these elements or these isotopes, these unstable isotopes, are going to decay. Now, I mentioned earlier that this is our graph and this is the band of stability, and all of whatever is in the green is going to try to decay to get to this line. So let's talk about each of these parts. Okay, and I have alpha emission up here, and I have positron emission and beta emission. Now that we know a little more about these types of decay, let's talk about how we can predict these, whether a particular isotope is going to decay by which emission. Okay, for elements that are heavy elements, so anything above this blue line over here, anything above that falls under this category is going to decay by alpha emission. Not to say that they cannot decay by these, because they do, but mostly the predominant mode of decay is going to be alpha emission. Why is that? Because every time an alpha particle is released, they reduce their Z number, the number of protons, by 2, and therefore they can quickly get to this band of stability line. So anything that's up here is going to undergo mostly alpha emission because they quickly reduce both the mass number by 4 and the atomic number by 2. So they do that quickly to try to get to this band of stability. Heavy elements, Z number larger than 83 or so, they decay by alpha emission. Mostly, they do these as well, but they decay by alpha emission. Now let's look at those isotopes that fall above the blue line here. If they fall above the blue line, that means that they have a larger number of neutrons than protons, and they need to reduce the number of neutrons to lower this curve to the blue line. They need to reduce the number of neutrons and increase the number of protons. The only way to do that is by beta emission, beta decay. We said when a nucleus undergoes beta decay, it converts a neutron into a proton, and therefore it increases the Z number, the atomic number. And this is what happens when you have isotopes that are in the above this line, this blue line, because they have a larger number of neutrons than they need, and therefore to reduce the number of neutrons they convert them to protons, and they do that by beta emission, beta decay, because they are expelling a high energy electron from the neutron and converting it to the proton. Those isotopes that fall below this blue line have a larger number of protons. If you think about it, they're closer to the protons, so they have more protons than they do neutrons. Here, they're closer to the neutrons, so they have larger neutron number than proton number. But those isotopes that fall below this line have a larger number of protons than number of neutrons. Therefore, they need to reduce the number of protons and increase the number of neutrons, or just reduce the number of protons. And they can do that by positron emission. We said positron emission converts a proton into a neutron because it expels it converts a proton by expelling a positively charged particle, and it converts the proton into a neutron, and therefore it's going to decrease the number of protons and increase the number of neutrons, bringing that ratio closer to this blue line. And this is how you can think about a particular isotope that falls under these three categories. So above this blue line over here are the heavy elements, and they decay by alpha emission. If you're above the blue line, you're going to try to reduce the number of neutrons and convert the neutrons into protons by beta emission. If you're below that line, you have a heavier number of protons than neutrons. You need to reduce the protons, and you do that by positron emission because it converts a proton into a neutron. How can we tell then, if we're given a particular isotope, how can we tell the mode of decay by just looking at the isotope? I have worked all of these examples for you on a separate video, so click on this and watch how to tell how each of these isotopes is expected to decay. Now, note that they can decay by, especially the heavy elements up here, they can decay by several different types of decay, but the main decay is going to be alpha emission. And once again, I've made this video for you. Watch it, and if you have any questions, let me know. This is the end of part 2 for the lecture on chapter 20.